Hi guys, thanks for stopping on A Piece Garage. I'm wearing a hat today because even though it's 65 in the shop, it's only 6 degrees outside. And I got to run out there, so got to keep my hat on. Anyway, this video is going to be about fastening. Fastening is one of my most favorite subjects to talk about, and no, I'm not nuts. Fastening, I think, is one of the most misunderstood aspects of any mechanical assembly. When you assemble something and use a fastener, whether it's a bolt with a nut on it, a screw, a plastic fastener, anything, a lag bolt, you're fastening something together. And what are you trying to do? You're trying to clamp something together. And one of the questions I get most often is, what happens if I put lubrication on a fastener? Can I put anti-seize on my head bolts? Could I use grease on my, I don't know, water pump bolts? But it's important to understand what happens during fastening and what fastening really is. When you go to put fasteners, put some lubrication on a fastener, and you go to torque something down. Because you can over-torque something and you can ruin a fastener, ruin a hole, galling, all kinds of things. So what we're going to do in this video is a couple things. I'm going to talk a little bit about theory like I always do, explain a little bit of the background about fastening, some of the concepts and what fastening really is, and then I'm doing an experiment. We're going to talk about theory up front, do an experiment, prove the theory right or wrong, and then we'll come up with a conclusion. That's what this is all about. And what I hope to do in this video is change your mind or change the way you think about fastening. Change the way you think before you put a bolt in and grab a wrench and reef on a bolt and really yank on something. Really think about it, because you could have dire consequences. And you strip a bolt, strip a hole or something like that, we know how aggravating that is. So let's go through some of the theory and then we'll do an experiment. So let's start talking about fastening by talking about the most common type of joint, and that's a tensile joint. A tensile joint is when we have two pieces. This could be a block and a head, whatever. Two pieces of material that you're trying to bolt together. You have a bolt that goes through with a nut. You could either have that or a threaded hole, whatever. But basically in a tensile joint you have some applied forces. And the applied forces are the things that are trying to rip the joint apart. Compression, pressure, something is trying to pull these two pieces apart, okay? Now, they're trying to separate the joint parts. And the joint performance, or the performance of this joint and this fastener, is a function of one thing: clamp force. Clamp force is what you're trying to apply to a couple of parts when you put a fastener in and torque it down. There are different kinds of spring rates for different fasteners, different kind of spring rates for different kind of joints, but in a basic type of joint, you have two parts with a fastener. There's an applied force that's trying to rip it apart, and when you torque on a fastener, you have tension in that bolt. The bolt is trying to be pulled apart. The bolt is trying to be pulled this way. It's pulling apart. As the bolt pulls apart, since there's tension, it pushes the two parts together. You get a clamping force, and this is what we're going to be talking about: clamping force in a joint and the function of the fastener in a clamp in a tensile joint. Now, as you torque, you put torque. What is torque? Torque, you're going to spin the nut on this joint, and the force that is reverse of that, or the resistance to rotation, is torque. That's what torque is: resistance to rotation. And the amount of torque that goes into a fastener to create the bolt tension is a lot less than you think. So, here's the question: dry versus lubricated. Do I use my fasteners dry, or do I put something on them to lubricate them, anti-seize so they don't seize up? And let me explain the difference, and this will be part of our experiment. Lubrication, or coating for lubrications, they fall into two basic categories. You have the integral lubricated coatings. These are coatings that come on your fastener. They can be either a zinc or cadmium plated bolt. So you have a bolt and it's got some kind of coating on it, black oxide, whatever. That coating is going to act as a lubricant. And there's also surface lubrication. This is where you put on your anti-seize, oil, wax, some kind of coating. If you're a carpenter and you put wax on a screw to help it go in easier, you're putting a lubrication on that fastener to help it go in. So that's a surface lubrication. So, before we get into the actual fasteners, let's talk a little bit about science. There's a coefficient of friction. The coefficient of friction, or the total friction of a fastener, is measured by this formula right here, and it quite basically is T stands for the tightening torque in Newton meters, F is the clamp force in kilonewtons, P is the pitch thread of your fastener, D2 is your basic pitch diameter, and DB, this is the effective diameter bearing surface, or the area underneath the head of the bolt. That's the formula for coefficient of friction. You would use this formula to start to calculate, if you know the base material, the tensile strength of your base material, this will help you calculate the yield point and how much angle you can put on a fastener to achieve the maximum clamp load. So this formula is kind of important. So here we have this is what our experiment is going to be based on, so I chose this. And these are the basic parts of a joint. You have your input torque, you're going to torque a bolt, you're going to screw a bolt in. You have two parts you're trying to clamp together. There's a clamp load, there's also, might be a clearance hole or not on one of them. The grip length. The grip length is between the bottom of the head of the fastener to where the threads start to engage. These are the engaged threads. Here's our grip length. There's usually a clearance hole, there might be an unthreaded shank, counterbore, whatever, but these are the clamp parts. And this is the part we're going to be focusing on. The bearing surface, the clamp parts, and the engaged threads. So, it's interesting to know that when you torque something down, 90% of the energy goes to overcoming friction. Overcoming the bearing friction, which is the area underneath the thread. 50% of the energy from torque goes into that part of the torque. The threads, overcoming friction of the threads is 40%. There's your 90%. 90% of your torque goes into overcoming friction. Only 10% of your torque goes into clamping the parts. That's pretty low. You would think that I torque something to 50 foot-pounds, I'm really putting that into clamping the parts, but that's not true. 90% of it's going to overcoming friction. And what does that mean? Here's a basic example. So let's talk about the torque curve. A torque curve is, if you were to take a bolt and we're able to measure the force or the applied force tension on a bolt, this is what the torque curve would look like, how the metal is performing. And I've showed this in other fastening videos that I've made. Torque is on this side, so this torque will be measured in foot-pounds or Newton meters, and angle is measured in degrees. So as you're turning a bolt, you're moving up the torque curve, okay? Now there's going to be a minimum here. The minimum is the minimum amount of torque you need to apply to that fastener, or else it's useless. It's going to come loose immediately. When you put something in and you have a spec, your torque spec, let's say in my example, the test we're going to run here, our experiment, we're going to use 20 foot-pounds. So let's say your torque spec is 20 foot-pounds. That is a calculated specification and is a calculated point on this curve so that you can take this fastener out and reuse it. Once you go to this point, once you go past this point, you're stretching it. That's a torque to yield fastener. So the torque is a calculated amount, and usually you shouldn't use a fastener more than 10 times. So this number is based on a calculation to put in and take out without damaging the fastener or the base metal around it. This green area is the yield point. So when you start to go past this point and the fastener starts to bend, so now I'm putting angle on it, I'm turning it, but the torque is not going up as much because the bolt is starting to, or the fastener is starting to bend. I'm bending the fastener. This is the optimum installed range. If you were to do a calculation, you'd want to end up somewhere in that area, and that's where your optimum installed area or range would be. If you go past that, if you start getting past here, now you go more angle on it, and you're starting here, you're going to start to get necking. And it's tough to see on this bolt, but you'll start to get necking. If you go even further still, you go past it, you can see how this bolt's starting to get necked down. You're going to start stretching the bolt, and you're getting past the fatigue point, and it's going to fail. Ultimately, your fastener is going to fail. It's going to crack, and that's because you've gone well past the yield point of the material and it fractures. That's what happens. Now, recognize what I want you to notice is this right here, this torque spec, where this dot is, because I'm going to show you some real torque curves here, and knowing where that point is important. So, proper bolt stretch. What does bolt stretch mean? Bolt stretch is a measure of clamp load. When you get it, here's the torque spec. When you tighten here, the bolt's not going to stretch. But if you put angle on a fastener, and you get over here, you're going to stretch this bolt. This bolt is going to start to stretch, and when you get in this zone for the optimum clamping length or the optimum grip strength of a fastener with the additional clamp load of angle, you're going to have some stretch on it. But what is the proper bolt stretch? There are calculations for that, and it varies on every fastener, base material, and there's millions and millions of combinations, so I can't go that. But there is a proper bolt stretch. Now, this is a real torque curve. And what this shows is a fastener. This blue line is the torque, or the resistance, measured with a transducer. And here's some being run down. So it starts at minus 300 degrees. So it's running in roughly one rotation. All of a sudden, it starts to see resistance. The torque is going up. In this particular case, the first part of this program is measuring the torque up to this 10 Newton meters right here. So at 10 Newton meters, the program switches to a different stage. It goes into this stage, and now it's going to monitor this. This green zone in a program, when you have an electronic tool, is where this line has to fall, or where we have to get our torque spec to in order for it to pass, to be a good rundown. If this were to be outside anywhere, if this were to reach 20 Newton meters anywhere over here, or it was trying to get past this point, that it wouldn't meet the torque spec, so that joint would fail. That's what torque curves are used to look at. And when you use electronic rundowns or electronic torque wrenches, this is what it's measuring right here. But if you remember I told you remember the torque spec, you notice how the curve is going up and it stops. It's not bending, it's just tightening up. So let's take a look at a torque curve now for a fastener that's a torque and angle curve, okay? There's a torque and angle. This has some preconditioning where it runs down the bolt and it loosens it up just to condition the threads. You want all the threads to be lined up, so to speak, so this is a preconditioned step in here. But here's the point I want you to see. Before this would be the point would be our torque spec, right? That's where our torque spec was, but we go past that. So now we're going past that and we're deforming the bolt. We're stretching it to achieve maximum clamp load on this fastener, and you can see how narrow this pass range is for this fastener, so that you can see a torque to yield fastener is going to have a much narrower range because you're stretching the bolt and you want to monitor the performance. That's what a torque curve looks like, okay? So let's recall this. Overcoming our forces. 40% in the threads, 50% in our overcoming the bearing friction, and only 10% goes into clamping. So what does that mean? Let's do a simple example here. If we tighten something to 30 foot-pounds, 40% of 30 foot-pounds is 12 foot-pounds, 50% is 15, 10% is 3. So when you tighten something to 30 foot-pounds, you're only getting 3 foot-pounds that actually goes into the torque of that fastener. So now the question is, if 40% goes into my threads, what happens if I put some lubrication on it? So if I put some lubrication on my threads, I'm going to reduce my foot-pounds to 11.75. Let's just say for an example. This is still going to be 40% of the force. So 11.75 is 40% of 16.45. This is going to remain the same at 15. This is going to remain the same at 10% at 3. So this is going to come out with lubrication. You're going to need 34.45 foot-pounds of torque to achieve the same clamp load as a 30 foot-pound dry fastener. That's what lubrication does when you put it on the threads. So, overcoming forces. What do we know about this? If we have a 3% drop in thread friction because we put a lubrication on there, we're going to have a 13% increase in torque required to maintain the same clamp load. You're going to hear me say clamp load a lot because clamp load is what we're trying to maintain here. Not torque, nothing else. The clamp load between the parts is what's important. So there are torque specs. There are charts online. You can look up different torque specs for bolts with lubricated threads, bolts for dry threads and standard foot-pounds. And when you compare them, let's say if we go to an 8mm, it's for a different fastener, 8G, 10K, 12K. It goes from 16 to 18 lubricated, from 22 to 27 lubricated, and from 27 to 31 with lubrication on the threads. So there are torque specs for fasteners if you're going to lose lubrication. Now, when people ask questions about torque, and if I put lubrication on my threads, you hear me, sometimes I'll respond and I'll say you're pushing, if you put lubrication on, you're pushing out the torque curve. So here's some normal torque curves of some normal fasteners. Here's the clamp force, so here's our clamp load at 25,000 newtons, okay? So here's our clamp force, and here's our angle. input angle. So roughly this one reached a clamp force at roughly, I don't know, around 52 or so, 56, something like that degrees. And the high end of the scale is 75, so the range is something like 52 to 75, right? If I put lubrication on all of these fasteners, this is what happens to the torque curve. It pushes it out. It takes more rotation to put the same clamp force on a fastener, and we're going to do this in an experiment. We're going to prove this right or wrong. So the difference is, what happens if I put angle? If I have a torque to yield fastener, and I'm going to go to angle, what happens when I put angle on it? Now, we're going to switch to angle. This is going to be angle. This is no longer going to be clamp force. We're going to be measuring something else. We're going to be measuring something called resultant torque. And resultant torque is the torque that is the resistance to rotation after the fastener reaches the applied angle. So when we take a fastener, turn it, when we get to an angle, how much force is being resistant there for torque. So now this is going to be resultant torque on the left side, angle in degrees on the bottom. And what's going to happen if we take these fasteners, dry, threads lubricated, and totally lubricated, and what happens to the resultant torque? Resultant torque is direct relationship to the clamp load. So when you put an angle on, the lower your resultant torque, the lower your clamp load. So here if we got a dry fastener, it's going to come up here and you're going to get a high clamp load. You see how that goes? It's going to start to yield. You put angle on it, and there you get your resultant torque up here. If we have one with just the threads on it, the resultant torque is going to be a little bit lower. And if we have lubrication on both, being the threads and the bearing surface, the resultant torque is again going to be lower. So here's a fastener with the same amount of torque on it, with the same applied angle, and it has a low resultant torque. Resultant torque is a measurement of clamp load. Clamp load is directly related to bolt stretch. Remember we talked about proper bolt stretch. Those are all related. So let's go do an experiment and see if we can prove all of that stuff correct or wrong. So here's our experiment. This is what I have. I have a block of steel clamped up here, and I have 3 fasteners installed. The first thing we want to prove is that the idea or the theory that you have to overcome 40% of thread friction, 50% of the bearing friction, and then 10% torque. We want to prove that to make sure that's a true theory. We're going to prove a theory. So what I have here is these bolts. There's 3 bolts, 1, 2, and 3, and this is what they are. I found 3 identical fasteners. They're all the same length, and this is going to be important in the second part of the experiment. They're all 841 thousandths long, every one of them. I measured all 3. The difference is this one is installed dry. This one has lubrication only on the threads. This one has lubrication on the threads and underneath the head. So if we were to prove that experiment, prove the first part of the experiment of the ratios, this one should reach torque. This one should take a little longer to reach torque, and this one should take even longer to reach torque, okay? Now, they're all 841 thousandths long. I measured them all, and the first part of the experiment is the same thing. So what I'm going to do is, the first thing I'm going to do is I'm going to torque all of these down to 20 foot-pounds. That's the first thing I'm going to do. And I'm going to measure, using my angle gauge here, I'm going to measure how many degrees it takes for each one of these fasteners to reach 20 foot-pounds. Okay? Then I will write it down so we know we have a good reference point. Now I'm going to do this carefully because I don't want to turn the fastener and put a false pre-torque on it. Okay, so I'm just going to sit it there, move my angle gauge. I'm going to zero it out. Okay, 0. Okay, now I'm going to torque to 20 foot-pounds. Okay, and as you can see, that one is right at 15, 16, 17, 18. This one took 18 degrees. 18 degrees? I'll do the same thing with this one. Let me just get this turned. Find a good spot. Okay, now this one only has lubrication on the threads, so it should take a little more than 18 degrees to tighten this one up. Okay, got it all zeroed out. Everything's nice and square. Let me go with this one. Okay, this one took 28 degrees. This one took 28 degrees. That is an 8, although that looks stupid. 28. Let me do the last one. Now this one has lubrication under the head and on the thread, so it should take a little bit more than 28. And there we go. Let me set it. We'll go to... And this one took 31, 33. 33 degrees. So we just proved the theory, the first part of the theory, to be correct. 18, 28, and 33. We just proved that in order to get all of these bolts to the same torque, now they're all torqued to 20 foot-pounds. Since the threads are lubricated here, I had to get the threads up to the 40% of the torque before it would go to the underhead, then to the bearing surface. That's why it takes more rotation. Now here I still had to get 40% on the threads, 50% on the bearing surface before the torque in the fastener would kick in. That's why it increases in rotation. So they're all tightened up to 20 foot-pounds. So we proved the percentage. So we know that's true. Now the next part of the experiment would be to prove that even though... So here's the question. Here's the real question. They're all at 20 foot-pounds. But they're not all at the same angle. It took more. This one's turned more than this one. This one's turned more than this one. They're all different. So when I lubricate my threads, what difference does it make? The difference is in the clamp load. That is why you have to put more torque on a lubricated fastener, is because you need to put more torque on the fastener to achieve the clamp load. Now I don't have a load cell here and I can't measure clamp load. I can't measure that now. But the second part of the experiment, I can measure clamp load by measuring bolt stretch. Remember we talked about bolt stretch? So what I'm going to do is I'm going to take all of these fasteners and I'm going to put on, well, let me write this. I'm kind of working around an angle. I'm going to put 35 degrees of angle on every one of these fasteners, okay? And so you can see that I'm really doing 35 degrees, and I'm going to be saying I'll put a line on these just so you can see that they're all going to be turned even. And what do I anticipate this proving? This is what I anticipate this proving. They're all going to be turned an additional 35 degrees, so it's about this much, about a third right there, 30 degrees. And what I anticipate is that the bolts will stretch less and less. So with more lubrication on the threads, lubrication on the threads, and under the head. When I put an angle on here, you will have, this bolt will stretch, this will stretch less, and this will stretch even less. That means with less bolt stretch, you have less clamp load on the part. So I'm proving clamp load by measuring bolt stretch. That's why I have them measured at 841 thousandths. So I'll put the angle on it, we'll take them out, and we'll measure them, and they should stretch less. So let me get I'll do my first fastener here. I get this set up. I'll put my meter or my angle gauge on 0. And now I will add 35 degrees of angle. It's a little bit more I gotta go. 30, there we go. There's 35 degrees on that one. Now I'll set this one up. Get everything nice and square. Set that 0. And I'll put 35 degrees on this one. Okay, and now I'll do the final one. Okay, and okay, here we go. 35 degrees. Okay, now they all have 35 degrees on them. So I have here my regular 3/8 ratchet with a 13 millimeter socket. Now whenever you tighten something on your engine and you take it and you get it tight and you do it by hand and then you reef a little bit on it just to make it extra tight, That's about 35 degrees of angle. Now this is what's happening when you put that little extra bit of force on there to tighten a bolt up. This is what happens when you try just a little more tight. I'm going to make it tighter. I'm just going to guess. So if our theory is correct, I'm going to take all these out of here. I'm going to measure the length. This one will have the most bolt stretch. This one will have a little bit less. And this one will have a little bit less. So I have my caliper here, my 4-digit caliper. So I'm going to measure in thousandths of an inch. This one was 841 thousandths. So I'm going to take this out. It's pretty tight. Let's measure the bolt stretch on this one. See how much this bolt stretched with that 35 degrees. I'll measure it. Okay. This one is now should say I'm just measured the same way. 845 and a half. So this one is 845.5. So this bolt stretched about what? 4.5 thousandths. So this bolt stretched 4.5 thousandths. Now let's take out this one. This one should stretch a little bit less because it has lubrication on the threads, and less bolt stretch means less clamp load on the part, even though it's torqued and has the same angle as a regular fastener. So let's measure this one. I'm going to measure the same way. $844.5. So this is 844. So this bolt stretched 1/1000th of an inch less than this one. And this one should be even less. So let's take this one out. And this one measures I'm measuring them both the same. Measuring on flat spots. I don't want to skew the results at all. Be as honest as possible. It's a little bit to hold it because it's got oil all over it. That's why it's a little slippery here. Okay. 842.5. This one is 842.5. So, what did we just prove? We proved two things. When you have a fastener and you put lubrication on the threads, or if you put lubrication on the threads and under the head, we just proved that you have to put more torque on it in order to achieve the same clamp load. How do we do that and how do we prove that? Well, we just measured it and we proved that the bolt stretch is less on a lubricated fastener than it does on a dry fastener. So much between the dry thread and the lubricated thread and under a head, we have a difference of 0.03 of an inch. So this bolt stretched 0.03 of an inch less than this bolt that was dry. That's what the difference is. That's what lubrication does when you put it on a fastener. So next time you go to put a fastener in and bolt up your engine, think about before you put that last little crank on it. Think about it before you put a little bit of oil on it. I'm not going to worry about it. Think about all that stuff because it's very, very important. So that was a pretty neat experiment. Let's look at our conclusions and what we can derive or conclude from our experiment. First, there are two types of lubrication. They either are from the coating on the fastener itself or from an oil or something you apply. The second thing is 90% of torque energy is used to overcome friction. Only 10% goes into the torque of the fastener itself. Oil or lubrication on a fastener requires a higher torque to achieve the same clamp force or the same clamp load. You put lubrication on a fastener, you're going to have to torque it to a higher torque setting to achieve the same clamp force as a dry fastener. Critical thing to understand. And angle. Angle is used to apply an additional clamp load. That's where you get your bolt stretch or the torque to yield fastener. Once you stretch the bolt and it's a torque to yield fastener, you take it out, you must throw it away because you've already stretched it. It's already been yielded. Okay? And oil. Oil or lube on a fastener lowers the resultant torque after an applied angle. You saw in the chart of the force traces, we saw in the experiment that we used the bolt stretch to measure clamp force. We put applied angle on a fastener. We had a lower resultant torque because we measured it through the stretch of the bolt. The more lubrication that was on the thread, the less the bolt stretched, meaning the less resultant torque was applied and the less clamp force was applied to the fastener. So there you have it, guys. That is fastening in a nutshell, as simply as I can explain it. And even though I explain it simply, it doesn't diminish the importance of recognizing what you're doing when you're torquing down a fastener, installing a fastener, applying angle, putting on lubrication, even choosing the wrench you're going to use. So next time you pull out your 1/2-inch ratchet, put a socket on there to install a 1/4 20 bolt, maybe even a 3/8 16 or something like that. You could use, you're strong enough to stretch that bolt. You stretch that bolt, ruin the threads, you're going to yield the fastener, and you have to throw it away. Could result in a failed engine, cracked head bolts, ripped out threads, all kinds of things. So I hope I helped or changed your mind or changed how you think about fastening. I hope this helps you understand fastening and gives you a little bit more information so when you go to assemble something or when you're talking about something, you understand the failure, you understand what you're doing, and you understand the results so you can be more confident that what you're doing will turn out exactly the way you planned it. You won't have any failures and it'll be successful. I appreciate you watching the video. I'll answer your questions if I can. Thanks for all your text messages and emails and comments. I love it. Thank you for everybody. Thanks for stopping by Pete's Garage.